Preparing for a robotics engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Walk me through the main subsystems of a robot you have worked on. I usually break a robot into sensing, perception, planning, control, actuation, power, and compute. For example, on a mobile manipulator, cameras and encoders estimated state, planning generated collision-free motion, and the controller converted trajectories into motor commands. The key is integration. A good actuator is useless if latency, calibration, or state estimation is poor. I always think in terms of the full loop, from environment measurement to physical action. While answering, focus on sensing, perception, planning, control, actuation, power, compute, and integration. Show that you understand the robot as a closed-loop system, not isolated hardware or software blocks. Question 2. How would you tune a PID controller for a robotic joint or mobile robot? PID control is often the fastest, reliable starting point. I begin with a low proportional gain. Increase it until the response is quick but not unstable. Then add derivative gain to damp oscillation. Integral gain comes last, mainly to remove steady-state error because it can cause windup. I also check saturation limits, encoder noise, and load variation. The final tuning is validated with step responses, trajectory tracking error, and repeated tests on hardware. Make sure to cover proportional, integral, and derivative effects, a practical tuning sequence, stability concerns, actuator saturation, noise sensitivity, and how you validate performance under real operating conditions. Question 3. What is the difference between forward kinematics and inverse kinematics? Forward kinematics maps joint positions to the robot end effector pose. If I know each joint angle and the link geometry, I can calculate where the tool is in space. Inverse kinematics works backward. Given a desired tool pose, it finds joint angles that achieve it. IK is harder because solutions may be multiple, singular, unreachable, or constrained by joint limits. In practice, I combine analytical methods where possible with numerical solvers and feasibility checks. In your answer, talk about joint space versus task space, how forward kinematics computes end effector pose, how inverse kinematics solves joint values, and why multiple or no IK solutions may exist. Question 4. How do you approach sensor fusion in a robotic system? Robots need sensor fusion because every sensor has weaknesses. Wheel encoders drift, IMUs accumulate bias, cameras struggle with lighting, and LiDAR can fail on reflective surfaces. I fuse complementary signals to estimate pose or velocity more robustly. For linear Gaussian problems, I would use a Kalman filter or extended Kalman filter. For more complex distributions, a particle filter may fit better. I also care heavily about timestamp synchronization, calibration, and covariance tuning. Be sure to mention why single sensors are unreliable, how fusion improves state estimation, common sensors like IMU, encoders, cameras, and LiDAR, plus filters such as Kalman or particle filters. Question 5. Explain SLAM as if you were discussing it in a robotics design review. SLAM means the robot builds a map while estimating its own position inside that map. The challenge is circular. Better localization improves the map, and a better map improves localization. A mobile robot may use LiDAR, visual features, odometry, and IMU data. Over time, drift builds up, so loop closure is important when the robot recognizes a previously visited area. I judge SLAM by localization accuracy, map consistency, compute cost, and robustness in real environments. While answering, focus on simultaneous localization and mapping. The circular dependency between pose and map, sensor inputs, loop closure, drift, and practical evaluation metrics like map consistency and localization error. Question 6. How would you design obstacle avoidance for an autonomous mobile robot? I would separate global navigation from local obstacle avoidance. The global planner gives a route to the goal, while the local planner reacts to nearby obstacles using LiDAR, depth cameras, or ultrasonic sensors. I would maintain a cost map with inflated safety margins, and account for the robot footprint and braking distance. For dynamic obstacles, the planner must update at real-time rates. If no safe path exists, the robot should stop, replan, or request human assistance. Make sure to cover perception inputs, local versus global planning, safety margins, dynamic obstacles, real-time constraints, failure modes, and how the robot behaves when the path is blocked. Question 7. What are singularities in robotic arms, and why do they matter? A singularity occurs when a robot arm loses the ability to move freely in one or more task space directions. Mathematically, the Jacobian becomes rank deficient, or poorly conditioned. Near a singularity, small end effector motions can require very large joint velocities, which creates tracking errors or unsafe motion. I handle this by planning paths away from singular configurations, using damped least squares inverse kinematics, monitoring condition numbers, and enforcing velocity limits during execution. In your answer, talk about loss of degrees of freedom, the Jacobian, high joint velocities, control instability, workspace limitations, and strategies such as path planning, damping, or avoiding problematic configurations. Question 8. How do you decide between using ROS and building a custom robotics software stack? ROS is excellent when speed, modularity, and ecosystem matter. It gives me drivers, visualization, logging, transforms, navigation packages, and a standard message passing architecture. For research or prototyping, that is a major advantage. For production, I look more carefully at real-time requirements, cybersecurity, startup behavior, dependency control, and reliability. Often the best answer is hybrid. Use ROS2 and proven packages where appropriate, but harden critical control loops and safety functions separately. Be sure to mention development speed, ecosystem support, message passing, tooling, real-time limitations, deployment constraints, maintainability, and when production systems may need selective customization or hardening. Question 9. Describe how you would debug a robot that behaves correctly in simulation but fails on hardware. I would first assume the simulation missed something physical. I would compare logs from sim and hardware for commands, sensor readings, timestamps, and state estimates. Then I would test subsystems independently: motors, encoders, calibration, frame transforms, power delivery, and network latency. Common gaps include friction, backlash, actuator saturation, noisy sensors, and incorrect mass properties. I like to reduce the problem to the simplest reproducible motion, fix one variable at a time, then revalidate the full behavior. While answering, focus on simulation to real gaps, calibration, sensor noise, latency, actuator limits, friction, communication timing, logging, incremental testing, and isolating whether the failure is mechanical, electrical, or software-related. Question 10. How do you evaluate whether a robotic perception model is good enough for deployment? I do not judge perception only by model accuracy. I start with the robot task. Missing a person may be far worse than detecting an extra obstacle. So I look at precision, recall, confusion cases, latency, and robustness across lighting, motion blur, occlusion, and sensor degradation. I also test on data from the target environment, not just curated datasets. Finally, I evaluate downstream behavior, whether the planner and controller remain safe when perception is uncertain. Make sure to cover task-specific metrics, false positives and false negatives, latency, robustness to lighting or occlusion, dataset quality, edge cases, hardware performance, and downstream impact on planning or control. Question 11. What is the role of the Jacobian in robotics? The Jacobian connects joint space motion to task space motion. Given joint velocities, it tells me the end effector linear and angular velocity. That makes it central for velocity control, resolved rate motion, inverse kinematics, and singularity detection. It also appears in force control because joint torques relate to end effector forces through the transpose of the Jacobian. In interviews, I frame it as the bridge between what the motors can do and what the tool needs to do. In your answer, talk about mapping joint velocities to end effector velocities, force relationships, inverse velocity control, singularity analysis, redundancy resolution, and why the Jacobian appears in both motion and control problems. Question 12. How would you ensure safety in a robot that operates around humans? Safety starts before code with a risk assessment. What can the robot hit, pinch, drop, or misclassify? I would design layered safeguards, including emergency stops, speed limits, force limits, safe zones, watchdogs, and fault detection. For human environments, perception must be conservative, and the robot should behave predictably. I also validate safety under abnormal cases, not only ideal demos. Where applicable, I would align with standards such as ISO 1028 or ISO TS 15066. Be sure to mention risk assessment, emergency stops, speed and force limits, redundancy, fail-safe design, perception reliability, standards awareness, testing, logging, and designing predictable robot behavior near people. Question 13. Tell me about a time you had to trade off mechanical design and software complexity. A good example is when a mechanism has too much compliance or backlash, and software is expected to compensate. I would first quantify whether control can realistically overcome it through feedback bandwidth and sensor resolution. Sometimes adding a better encoder, stiffer bracket, or mechanical guide is cheaper than writing complex compensation logic. I try to make the trade-off at system level. Reliability, cost, maintainability, and performance matter more than proving one discipline can solve everything. While answering, focus on a concrete example: the engineering trade-off, cost, reliability, sensing or control burden, collaboration with other disciplines, and how you justified the final system-level decision. Question 14. How do you handle real-time constraints in robotic control software? For control, timing consistency can matter as much as average speed. I define the required loop rate, such as 1 kHz for low-level motor control. Then measure latency and jitter under realistic load. Critical loops should avoid blocking calls, dynamic allocation, and heavy perception work. Depending on requirements, I might use a real-time operating system, real-time Linux, microcontrollers, or dedicated motor drives. Non-critical tasks like logging and visualization should be isolated from safety-critical control paths. Make sure to cover control loop frequency, deterministic timing, latency, jitter, operating system choices, priority scheduling, separating non-critical tasks, and measuring timing behavior rather than assuming it works. Question 15. If a robot misses its target position repeatedly, how would you diagnose the root cause? I would first determine whether the error is systematic or random. A consistent offset points to calibration, coordinate frames, tool center point definition, or encoder scaling. Variable error suggests backlash, compliance, poor tuning, sensor noise, or slipping. In your answer, talk about separating systematic error from random error, checking calibration, transforms, encoder readings, controller tuning, mechanical backlash, payload changes, sensor drift, and using data-driven experiments. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.